This paper has a dozen authors, and if we listed all of the authors of Open vSwitch, then it wouldn't fit on the page because we have over 100 contributors. So let's start out with a few words about Open vSwitch. My guess is that a lot of the people here already know a fair bit about it. I'm not going to actually read this to you. It's worth noting that we're going to focus on use of Open vSwitch in virtual environments, although it supports other environments too. Let's talk a little bit about where it's used and how it can be used. So it's supported on a lot of operating systems with a lot of virtual machine environments and cloud management systems, and it's widely used in a lot of those. It also has been pretty popular in research for the last couple of years. If you type Open vSwitch into Google Scholar, then you can find well over 1,000 citations for it. And our mailing lists, the developer and discussion lists, have over 1,000 subscribers. So let me start out by telling you a little bit about how Open vSwitch is structured. So the green components there are the pieces that are actually part of Open vSwitch. So starting from the left, we have OVS DB server, which is very much just a database server. We use it to keep track of and control the configuration of Open vSwitch. It talks remotely over the OVS DB protocol to a remote controller that manages the network centrally. The second component there, OVS vSwitchD, is the daemon that actually does the network switching and the data plane components of the switch. It connects also to that same controller remotely over the OpenFlow protocol, which is the main protocol we use for data plane configuration. So vSwitchD controls the network through a fast path, and today I'm going to talk about it mostly in the context of the fast path that runs as a Linux kernel module, although there are other fast paths that use, for example, the Intel DPDK. And then at the top and the bottom of the diagram, you can see that the kernel module directly talks to virtual machines on the hypervisor and to physical NICs that lead out of it. So the use case that I'm particularly interested in today is network virtualization. So let me say a little bit about what I mean by that. So virtualization is probably familiar to a lot of the people in the room. Virtual machines provide a software version of a physical machine, but until recently, those virtual machines tended to be connected directly to physical networks, and that means that you have all of the restrictions of the physical network. It's difficult, for example, to migrate virtual machines between data centers and sometimes even into different parts of a single data center. Well, network virtualization adds another layer to abstract your virtual networks from your physical ones. And you can use it to implement logical networks that have logical switches and logical routers. And the VMware network virtualization controllers, NVP and now NSX, implement these logical networks as OpenFlow pipelines in Open vSwitch. So you can see here a conception of how it works. When a packet comes in from a virtual machine or physical node, it passes through a series of OpenFlow tables in an OpenFlow pipeline. So just to give examples of what some of these tables might do, your first table, table 0, might do logical to physical translation, figuring out where this physical packet fits in your logical network. And your second table might do an L2 lookup within the logical space. And then it would filter through and implement switches and routers as you configured your system to do. And then in the final table, it might translate the logical abstractions back into physical ones and send the packet out. So this works out very well. but it has some pretty serious implications for forwarding performance. Each of these OpenFlow tables is a general purpose table lookup that could be, in principle at least, quite complicated, and so you need a general purpose packet classifier for this. So there are many ways to implement packet classifiers for a number of reasons. vSwitch uses what's called a tuple space search classifier. So there's a lot of details we could talk about with those, but the important fact for performance is that a tuple space search classifier requires a number of hash lookups. That might be as few as one. It might be 10 or more. It depends on how the flows in the classifier match. So if you sum this over all of these tables in your pipeline, you might need 100 hash lookups or more to implement this series of 25 or so tables, which is typical for NVP or NSX. So that's slow is the summary, because and you can't really expect to get good performance out of a complicated pipeline with that many hash lookups per packet. So I'm not going in chronological order here in terms of how we implemented these things. Here are some of the things that helped with forwarding performance. We added multi-threading to user space. The Open vSwitch kernel module has always been multi-core and multi-threaded. We even implemented some fairly advanced forms of synchronization for user space, including a user space read copy update library. We added some fairly aggressive batching of packet forwarding. We optimized our classifiers in a couple of ways, and the paper talks about those. And we did several micro optimizations throughout the switch. So if you added up all of these optimizations that we did, well, it might have helped by, say, 100% or more in terms of packet forwarding performance, but that's not nearly enough. We needed packet forwarding to be, say, 10 times or 100 times faster, not 100%. So the summary, the bottom line is that all this classification is expensive on general purpose CPUs, and we needed a better way to do it. So we found ourselves implementing caching. And caching is often not used that much in networking because, in my experience, networking people, switch people are very concerned about worst case performance. And partly that's because a lot of networking components are dedicated resources. You have a particular appliance, and as long as you forward packets at the desired rate, nobody cares whether you use 100% of your CPU, 100% of your memory. Virtualization is a little different because the virtual switch is sharing the resources with the virtual machines. And so if you're spending CPU time on switching, then you can't spend that CPU time on getting things done in your virtual machines. So our first cache was very simple, based on the concept of microflows. So a microflow, in a network sense, is an individual stream of packets through the network. And from the viewpoint of packet headers, it's the complete set of the relevant packet headers and the metadata. So the nice thing about a hash table or a microflow is that it's really easy to throw it into a hash table. So we did that, and you can see the cache design here. So the first packet in a microflow going through the system caused a miss in the microflow cache, and then we would send that to user space, and user space would throw it through all those flow tables I was telling you about, and then it would add an entry to the microflow cache so that any later packets in the same microflow would just look at the cache, and they would only suffer one hash lookup instead of the 100. At the bottom, you can see that in theory there could be another level to the cache where we send a packet to the OpenFlow controller. But in practice, we don't use that in our network virtualization systems, so I'll leave that off the rest of the slides. So this gave us a really big speed up. The microflow cache helps greatly for those packets after the first packet. Everything is 100 times faster, and that gave us the 100 times speed up that we needed. So that was good enough until around 2012, and at that point we realized that there were fairly important workloads where it was not good enough. And it took us that long to figure this out. We had started Open vSwitch in, say, 2008 or so. It took us this long to figure that out because, up till then, we'd been testing things in-house. We had turned things over to customers, but those customers were mainly running test workloads. They might have let some of their special customers, our customers mainly being service providers, they might have let some special customers run some test workloads on it too, but there wasn't much production traffic. And then around 2012, we started getting production traffic through these systems, and we found out that maybe 5% of the traffic did not do well at all with the microflow cache. And that was fundamentally because there was a low hit rate. All of this traffic showed patterns where your microflows had 1 packet or 2 packets. And so we had actually a fair amount of overhead from populating the microflow cache, and then we got little or no benefit from it. So we needed a new kind of caching. So the way we started thinking about that was that being able to change from 100 hash lookups to 1 was great, but if we could instead change from 1 to 2 or to 3, that's still a huge improvement. So we came across the idea of, instead of using a microflow cache, to what if we were able to take the cross product of all of our open flow tables, so that you end up with a single flow table that combines the matches that you would have in all of your open flow tables. So this, in theory, would work out really well because usually some of these tables match on the same things, and the cost of a single classification, even across all those fields that all of the tables look at, is still much, much lower than the cost of doing all the classifications sequentially. The downside, on the other hand, is that combined table would have as many flows in it as the product of all of the flows in the other tables at maximum. So that's a ridiculous amount of memory, and there was no way we could afford that. So the next step was to realize that you don't have to compute that cross product in advance, that instead you can take a lazy approach to populating the cache. And in fact, that's what Open vSwitch did. So if you have a packet, for example, that arrives, and it matches on, say, IP source A and IP dest F and ETH dest I, then you can you can compute a megaflow cache entry that's just for that and populate it into the megaflow cache. And the result is that you get something that requires the same number of table lookups, or sometimes fewer even, as the naive cross-producting approach. But traffic locality allows you to have a practical cache size, and you still get most of the benefit. So like that, what we ended up with in terms of cache hierarchy looked a lot like OVS with the microflow cache, except that now we used flows that are much more general purpose. They look like this cross product, and we called these mega flows just because we had way too much confusion with with just the plain term flow. It was used for far too many things in our system. So megaflows worked well, but they needed a few refinements. So first of all, the approach that I've described so far, if any of your OpenFlow tables match on a particular field, then the resulting megaflows will always match on that field also. And if you end up with megaflows that match on, say, TCP ports, then the cache effectiveness of those is almost like microflows. Because a particular TCP port is only used for a few packets in many cases. So we needed an algorithm for generating megaflows that matched on as few fields as possible, because then the megaflows are as effective as possible. This is actually what I consider to be the biggest contribution of our paper. And if you're interested, I recommend going and reading section 5, which explains all the optimizations we came up with in detail. But there's not time to describe them today. So here's a summary. With the microflow cache, the first packet in a microflow requires lots of lookups, but later packets, only one lookup. On the other hand, for the megaflow cache, we have a larger than one number of lookups for almost every packet. Now, that means that the megaflows actually perform worse in the common case that the microflow cache optimized for well. And it would be better if we could get the best of both worlds by doing a small number of lookups for the first packet in a microflow and just one for later packets. And we came up with that by combining the two forms of caches. So in this, which is what Open vSwitch uses today, we have a first layer of caching that caches microflows. If there's no microflow cache entry, it falls through to the megaflow cache and does a lookup there with a small number of hashes, and then populates it into the microflow cache. And if even the megaflow cache misses, then it goes to user space, puts it through all of the OpenFlow tables, and then populates the megaflow cache and the microflow cache from that verdict. So that's what I'm planning to say about Open vSwitch and its caching. But I have a couple of parting thoughts before I finish. So I think a lot of what I'm talking about here arises from an architectural tension that expressibility is sort of the enemy of performance in many cases. The more general you make the system and the criteria that it can accept and the constraints that it can accept, then the harder it is to make it perform well. So OpenFlow is a good example that it's quite expressive, but at least in the case where you have many tables, it's difficult to make it fast on general purpose hardware. And that means that if you have high performance requirements, that might make applications avoid using OpenFlow to implement them. And as I've shown today, the caching at multiple levels allows OVS to resolve this conflict between expressibility and performance. We can make even these quite expensive series of flow tables implemented efficiently. And this allows the applications that run on it, NSX and NVP and others, to run fast. And in fact, the specialized versions of them would likely be slower. So in summary, we started from a very general purpose problem of making complex open flow tables fast, and produced what is, in my opinion, better results than if, say, we had started out just deciding to write a specific switch that implemented, say, what NVP needed. Thank you.
I'm Masood Moshe from USC. So I think one of the motivations of using the tuple search in OVS was to have very fast update for the rules, right?
I'm having trouble hearing the question.
So the motivation for having a tuple search in the slow path was to have very fast update of the rules.
Oh, yes. Tuple space search is used to allow the flow tables to be updated very quickly.
Okay, but then we have multiple levels of cache. Then how invalidating these cached entries work with fast rule updating?
So most flow table updates, in our experience, don't actually affect the disposition of most of the microflows and megaflows through the system. So we're somewhat lazy when it comes to cache invalidation. There's a section on it in the paper, but our main approach is that when the OpenFlow table changes, we go through the caches in a process we call cache revalidation, and we basically check whether the flows need to be treated differently, and if they do, then we update them.
Subhaya from Google. How does it handle the large SYN-flood attacks or DDoS attacks in case of cache thrashing? Does it fix the problem? Like, for example, you get a lot of SYN-floods with a lot of packet spoofed IP ranges or spoofed port numbers. How do you handle this cache thrashing?
Could you repeat the question? For some reason, the speakers are really hard to hear from right here.
Okay. The question is, I think the problem that cache is solving, you presented like caching layers, microflow cache and megaflow cache. In case of SYN-floods, a lot of spoofed IP source IPs or spoofed port numbers, then you have a lot of cache thrashing. A lot of flows come in, but you'll never get a hit. How do you solve this problem?
Oh, okay. I think you're asking about if, for example, there's something like a port scan that
Yes.
accesses a lot of unique ports.
Yes.
Usually that sort of thing would be covered by a small number of megaflows. We work pretty hard, for example, to ensure that it doesn't take very many megaflows to cover the entire TCP port range. So what would commonly happen is that we'd install one or two or a few megaflows, and that would cover the whole entire port scan.
Thank you.
All right, let's thank Ben.